D1. D2.
So there are some questions that we might want to ask, and the usual questions that people want to ask are, is climate change really happening? Should I be worried about it? What are my own CO2 emissions? And what can I do to make a difference? And that's pretty much, you can sum up everybody's questions in those four, and I hope I'll be able to give you some answers in some way. The first thing really is to ask ourselves whether climate change is happening. Well, there's various ways of looking at this. One way, which I rather like, is simply to look at historical levels of carbon dioxide in the atmosphere. And what's really quite nice is that there's pretty much global agreement. All of the different colours of dots on this graph are different people's measurements from around the world, from different countries, different institutions. And it's remarkable how good the agreement is. What is extraordinary is the date when it appears that this curve has started to rise corresponds with the invention of the steam engine. Now, that might be a coincidence, and there are people who say that it is a coincidence, and actually this is all due to volcanic activity or sunspots or something or other. Well, that's fine. It may be a coincidence. But there are other things that you might wonder about, whether they're also coincidences, but there are just too many coincidences for my liking. Another coincidence is that associated with carbon dioxide rising is global temperature rising. Now, the two things are independent, but it turns out that you can do some sums to work out that if CO2 levels rise, then sometime later you get temperature rise. And we notice from around the time back here when CO2 levels started to rise, global temperatures haven't really shown much, but they've begun to rise over the last few decades. And this is completely consistent with the CO2 levels. Now, the question is whether we should be worried about this. The question is, where's this curve going? Well, we don't really know. It could be going this way, or it could be going up this way, or perhaps it's going to turn around and come down. But no scientific evidence exists that's consistent with what we've seen so far that predicts anything lower than this level here. And that means that by the end of this century, we will have global temperature rise, which is a good 2 degrees more than it was a century ago. And 2-degree temperature rise represents significant change to the climate, change to sea levels, change to temperatures, agriculture, rainfalls. And that's the low estimate. This is a pretty good estimate, and this is a high estimate. Now, this 2 degrees is above the temperatures around about now, but actually historically they were lower. 4 degrees would be catastrophic. 4 degrees will melt the ice caps. Once we've melted the ice caps, then actually the ice caps are a refrigerator for the planet, and that refrigerator, essentially warm air from the equator rises, it circulates around, it descends around the equator, gets around the poles, it gets cooled, and that's nice. Also, the whiteness of the ice caps reflect sunlight, the albedo effect, and that helps to keep things cool. If we lose the ice caps, then the circulation will be changed dramatically, and we don't get the cooling effect, and there will be what is called runaway global warming. The oceans will warm up, the organisms in the ocean will die, and a lot of those organisms in the ocean are responsible for absorbing CO2, so there'll be even greater CO2 rise. So once that happens, we're in big trouble. So we must avoid this high level up here. But even this is pretty bad. We're not going to be happy with the loss of glaciers and the change of climate, the desertification of many countries. There'll be mass migration, there'll be mass crop failures, mass water shortages. So it's not a very nice scenario. So what can we do about it, and what should our thinking be? Well, this picture is quite an interesting one. This looks like a picture of the night sky, but in fact it's not a picture of the night sky. This is a picture of the United States taken at night. And there are all the lights from the cities in the States. This is a picture of Europe taken at night, and there are all the cities. Every one of those little dots represents a source of a huge amount of CO2, because we as people are responsible for that CO2. If you go in the countryside, there's very little CO2 being generated there. Well, you might think there's lots of crops and things and so on, and the farmers are generating CO2 with their machines, but they're generating it for us that live in the cities. So you can think of the CO2 as actually coming from each of those dots. How much CO2? And this is a question which we need to know the answer to, and everybody should know, have a feel in their minds for how much CO2 we're talking about. Now, that suitcase on the left is a very heavy suitcase. It's too heavy to check in on a plane, 30 kilograms. It weighs about the same as this pile of bricks here, about 30 kilograms. It weighs about the same as a full wheelie bin, 30 kilograms. How long does it take you, an average person in the UK, to generate that amount of CO2? Is it 30 kilograms in a month? Is that conservative? Does anyone know the answer? What do you reckon? Who'd like to hazard a guess? Is 30 kilograms in a month a good estimate? Who's got a... More or less. It's actually not even 30 kilograms in a week. It's 30 kilograms in a day. That is how much CO2 we are individually responsible. That amount there. Now, if you put 30 kilograms a day into your wheelie bin, that's per person. Per household, say, average household of 3 or 4 people, whatever, that's 100 and something kilograms a day. That's 700, maybe a ton a week. 2 tons in 2 weeks. We have garbage collections every 2 weeks where I live, and the garbage people would simply refuse to take away 2 tons of rubbish. Yet we quietly puff out 2 tons a fortnight of CO2 without thinking about it. Now, where do we puff it out? We puff it out. Oh, by the way, it's this number of bricks per day. Well, it means that there's about 1 brick every 2 hours. And people think, oh, well, we can suck CO2 out of the atmosphere. We'll find a way of doing that. Well, trying to find a way of sucking CO2 out of the atmosphere, if I were to give you a certain amount of money, you have to find a way of paying somebody to remove this much CO2 every 2 hours for your whole life. And it's probably going to get worse. Who are you going to pay to do it? And how much do you think you should pay them to do it? It's not obvious that there's even a method to do it. And that's what's scary about it. We sort of feel science will come to our rescue, but there is no science that will do it, and the magnitude of the problem is far too big.
D3.
And that's the low estimate. This is a pretty good estimate, and this is a high estimate. Now, these 2 degrees is above the temperatures around about now, but actually historically they were lower.
D4. Extract 1.
What's really quite nice is that there's pretty much global agreement.
Extract 2.
What is extraordinary is the date when it appears that this curve has started to rise corresponds with the invention of the steam engine.
D5.
Okay, temperature's been rising since the invention of the steam engine. CO2 has been rising then. Temperatures have followed suit, and we're doubling CO2 every 60 years. Coincidence? Okay, maybe, but I sort of have a nagging feeling that it might not be a coincidence, and I'd like to think that my children and grandchildren have a decent planet to live in. So I think, as an insurance policy, we should probably take this seriously. I'm not certain, but I'm not certain that my house is going to burn down either, but I've got insurance for my house. In fact, the chances of my house burning down are pretty negligible, but I pay for insurance. So I should pay for this insurance too. So we can't just rely on the trees and the oceans to suck it up, because they can't suck up this kind of quantity. It's simply not enough. So who's responsible? Now, David Mackay's book has got all of these graphs in it, and it's just wonderful because it helps us enormously to put numbers on, to quantify things. So along here, the bottom axis is population. So, for instance, this block in here represents the population of China. And China, on average, is pumping out about 4 tons of carbon dioxide per year per person. Now, you can do a little calculation. The area of this rectangle represents China's CO2 output. So area is what matters on this curve. So that means this rectangle here is the US population down across the width, multiplied by the US generation per person. The area is what matters. So we can see that the US area here is comparable with China. And here's India, Indonesia, Pakistan, Japan is up there. The United Arab Emirates is up there. Australia is up here. But let's suppose the whole planet was to aspire to a lifestyle like ours. There's the UK, or like America's. That means filling up this whole rectangle. And we're not sustainable now. That is not sustainable. If we wanted to average everything out, well, that means averaging out roughly about where China is, actually. But actually, where we've got to aim for globally is this line here. How we're going to get there? Well, that's, I suppose, what the subject of the rest of this talk is. There are governmental agencies that like to advise us on how to do things. This is a line representing how many tons of carbon dioxide per year per person we should be generating in the future if we're going to avoid catastrophic climate change. This purplish line here says, well, if we stay as high as that, then we've got a 16 to 43% chance of greater than 2 degree climate change, which is no good, really. Here, the chance is 9 to 26%. The rather annoying thing is that the actual curve that the government is wanting us to follow is above both of those. So they're ignoring scientific advice and saying, oh, well, we'll just do the best we can. We won't achieve what we want to achieve. And the reason we won't achieve it is because we don't really want to. We don't like nuclear power stations. We don't like wind turbines. We love our countryside. We love our beaches. We love our lifestyle. So what are we going to do? Well, okay, let's think what we can do. The great thing about David Mackay's approach is that if you can add things up, it's like budgeting for a holiday. So, like, I've got £1,000 and I'm going to go for a holiday. So, where can I afford to go? That's what we do, isn't it? Well, I've got a certain amount of CO2 that I'm allowed to emit. How can I emit it? Let's do some sums.